Hello and welcome to BYJU'S JEE Advanced video series. My name is Mrinal and today the topic that we are going to cover is thermodynamics. So how we are going to go about this video is, first we'll do a quick analysis of the questions that have come in previous year's JEE Mains and Advanced exam, and then we are going to solve some really cool problems. So while watching this video, if you genuinely feel that you have learned something and if we were able to help you in some way, then please subscribe to our channel and hit the bell icon. So if we talk about JEE Advanced exam, just last year 2018, 3 questions were asked from this topic. So one question was from cyclic process, one was from adiabatic process, and one was from PV diagram. Now in 2017, again 3 questions were asked, and one was from adiabatic process, and one was from first law of thermodynamics, and the last question was from again PV diagram. In 2016, if you see, 2 questions were asked from this topic. So one question was from first law of thermodynamics and another one was from adiabatic process. 2015, only one question was asked, and that was on first law of thermodynamics. And in 2014, 2 questions were asked. One was asked on first law of thermodynamics and another one was based on the PV diagram. If you look at the JEE Mains exam, 2018, only one question was asked, and that was from adiabatic process. In 2017, again one question was asked, and that was based on the ideal gas equation PV is equal to nRT. 2016, again one question was asked from PV diagram. 2015, 2 questions were asked. One was from second law of thermodynamics and the second was from adiabatic process. And in 2014, no question were asked. So if you see overall in this topic, we can consider that the PV diagram, adiabatic process, first law of thermodynamics and second law of thermodynamics are quite important. So in this problem, we are given a pressure cooker, all right, and there is some gas inside the pressure cooker which is at a temperature of 27 degrees Celsius, all right, and the pressure is also mentioned, is given to us as 10 to the power 5 Pascal, fine. Now we have a lid at the top and there is a vessel, all right. The vessel has got some mass, okay. So the question that is asked is, at what temperature will this vessel just get lifted up? Okay, so this is what is being asked in the problem. Okay, so let us see how we solve this problem. Now if I think about this problem, I can think, okay, there are like certain variables. There are like temperature, we have pressure, and we have initial condition and we have a final condition, right? So if I can think about an equation which relates all of them, that's the ideal gas equation, right? So I can write, let us say directly I can write like P2V2 equals to nRT2, right? So these are the final values of my pressure, volume and temperature. So I want to know this T2, right? So if I write T2, I'll get T2 is equal to P2V2 upon nR, right? So since it's a pressure cooker, the volume remains same, that we know. Cool. The next thing is, there are 2 unknowns in this. The first thing is I don't know this P2 and I also don't know this number of moles, correct? So if somehow I'm able to calculate these 2 values, I'll be able to plug in this and I'll be able to measure my value of T2, correct? So how do I calculate number of moles? I'll calculate number of moles by using my initial condition. So what was the initial condition? Initial condition, if I write P1V1 is equal to nRT1. So do I know P1? Yes, I know because it's given to me in the question. That's 10 to the power 5. V1, we can just take it as V, as the volume of this pressure cooker, which is not going to change anyways. N is what I'm supposed to find out. R is a constant and T1 is given as 27 degrees Celsius, which is nothing but 300 Kelvin, right? So I can write N is equal to P1V1 upon RT1. If I just plug in the values, I can write N is equal to P1 is 10 to the power 5 into V1. I'll just keep it as V because later on also we are going to encounter a V. So there is a chance that they might cancel out. So I'll just put V over there. R also you might get it at a later stage, so I won't cancel this. And into T1 is 27 degrees Celsius, which is equal to 300 Kelvin. Cool. So I get the value of N. All right. So I have figured out N. Now what about this value of P2? So P2 is the pressure which you get when this vessel just gets lifted up, right? So when this vessel will get lifted up, the pressures that are acting, or the pressure balance, will be the atmospheric pressure and the pressure due to the weight of this vessel will be equal to the pressure of the gas, and that is my P2, right? So if I want to calculate that, I can write P2 is equal to P atmospheric or P naught plus weight of this per unit area, right? So if I put the value, that will be 10 to the power 5 plus mass is given to us as 100 grams. So I can write it as 100 into 10 to the power minus 2, sorry, 10 to the power minus 3. It will be equal to 10 to the power minus 3 into acceleration due to gravity, that's 10, and the area is given as 0.1 centimeter square, so that will be equal to 0.1 into 10 to the power minus 4. Cool. Now if you see, it's 100 into 10, that's 10 to the power minus 3, and 10 to the power 3, they will get cancelled out, right? If I move this 10 to the power minus 4 in the numerator, I get 10 to the power 5, so I get finally 2 into 10 to the power 5 pascals is the value of my P2. Now I'm almost sorted with everything, all the informations that I require for solving this problem. All I need is to substitute the values. So if I write T2 equals to P2, which is equal to 2 into 10 to the power 5 into V2 is just V, because the volume does not change, divided by R into number of moles, right? So number of moles is 10 to the power 5 into V, and then R into 300 comes in numerator, right? Now let us see what all things gets cancelled out. So you can cancel V and V, you can cancel 10 to the power 5 and 10 to the power 5, you can cancel R and R, so you're left with T2 is equal to 600 Kelvin, and 600 Kelvin is your correct answer. So in this question, we have been given a cylinder, and this cylinder consists of an ideal gas. It also has a movable piston, and this piston has got some mass on it, right? Now, the thing is that this ideal gas is at 30 degrees Celsius, and what we are going to do is we supply heat. All right, so we supply heat, the gas gets heated up, and the temperature of the gas becomes 100 degrees Celsius, right? And we stop there. Okay, so this is the first situation that's given to us. In the second situation, what it is told is that as we supply heat, the piston will be moving, right? So when the gas reaches to a temperature of 100 degrees Celsius, during that time, the piston moves by a distance of 20 centimeter, all right? And then we don't allow the piston to move at all. So we fix the piston, and then we start cooling off this gas. So as we cool off this gas, then the temperature of this gas will go on decreasing till it comes back to its initial condition, that is 30 degrees Celsius. So in first case, we are supplying some heat and we are raising the temperature from 30 to 100. And second case is we have fixed the volume, and then we take off the heat and we cool the gas from 100 degrees Celsius to 30 degrees Celsius back again. All right. The question that is asked from us is how much will be this difference in the heat energy or the heat energy interactions for both the cases? That's what being asked from us. So how do we solve this problem? How do we go about solving this problem? Now let us analyze each of these conditions one by one. So first case, we have been told that some amount of heat is given to the gas. Now what happens when you supply heat to a ideal gas? Basically the temperature of the gas is going to increase, right? And also since it has got a movable piston, the piston is going to move upwards, right? So we have got some amount of work done, right? Because the piston is movable. Second is there is an increase in temperature because we are heating the gas. So two things are happening. The temperature of the gas is increasing and we are getting some amount of work done, right? So the change in temperature relates to something that we know, that's internal energy, right? So internal energy is changing, we are getting work done, and we are supplying heat. So what is the equation that relates all the three? It's obviously the first law of thermodynamics, right? So we should start with writing the expression for first law of thermodynamics. So let us say that I take delta Q1 as the heat that is supplied, delta U1 is the change in internal energy because of the change in temperature, and delta W1 is the amount of work done while the piston moves. So how much the piston moves has also been given to us in the question, and that is equal to 20 centimeters, right? So the piston moves by a distance of 20 centimeters. Cool. Now if I just rewrite this expression, I can write delta Q1 equals to delta U1 plus delta W1 can be written as P times of delta V. right? P times of delta V. That's displacement work. So in this, we need to know P and we need to calculate delta V. Then only we'll finally come to this expression of delta Q, and that is what is the requirement of the first condition, right? So how do we calculate this P? That's the pressure of the gas. If you just think slightly that what happens when the piston is moving upward, right? Why will this piston stop? A point will come when the pressure on both the sides of the piston will become equal. Now, the downward direction, if you see, it is below the piston, it's gas, right? And at the top, it's atmosphere, and we have also been given that there is some mass of the piston, right? So what happens is, if I draw a diagram like this of the piston is going to stop when it reaches to a point of pressure balance. So at the top, there is this P0, which is atmospheric pressure, and also since this piston contains mass, the weight will be acting per unit area, so there will be a pressure also because of the weight of the piston. And how much will be that? How much will it be? It will be equal to mg upon A, right? And from the bottom there will be pressure of the gas, right? So if I can balance this, I can write this expression as P is equal to P0 plus mg upon A, right? P0 is given to us, that's atmospheric pressure, that's equal to 10 to the power 5 Pascal, plus M is given as 8 kilograms into G, we can take it as 10, and area is 60 centimeter square. So we can convert this into meter square. We can write 60 into 10 to the power minus 4. Okay. Now, if I just calculate that, I move this part in the numerator, and then I get 10 to the power 5 plus 8 upon 60 into 10 to the power 5. 10 to the power 5, I can take it as common, and I get 1 plus, and if you calculate 8 upon 60, you get 0.13. So you get 1.13 into 10 to the power 5 Pascal. So that's the value of the pressure inside. All right. So that's the pressure of the gas. All we have to calculate for work done is change in volume. Now, how much will be this change in volume? Change in volume is equal to area times of displacement. So area is also given to us, right? And also the displacement is given to us. The displacement is 20 centimeters because the piston gets displaced by a height of the piston gets displaced by 20 centimeters, right? So what we can write, delta U1 plus, we just plug in the value for pressure, that's 1.13 into 10 to the power 5, and then we have delta V. Delta V is area times displacement. So what was area? 60 into 10 to the power minus 4 times displacement was 20 centimeters, that's 0.2 meters, right? So I can write this as delta U1 plus, if you calculate all this, you'll get approximately 136 joules. So that's my Q1. So I have calculated in the first situation how much is the energy given to the gas to heat it from the temperature of 30 degrees Celsius to bring it to a temperature of 100 degrees Celsius, right? Now we go about calculating in the second part that when you fix this, when you fix the piston and you don't allow the piston to move, right? And then you cool the gas back from 100 degrees Celsius to 30 degrees Celsius, how much of heat will be given off from the gas, right? So this is what basically we have to calculate now, right? So first part of the question is done. Now let us see how do we do the second part of it. So now in the second situation, the piston is already up there. The temperature of the gas is 100 degrees Celsius. And we are extracting heat, but we are not allowing the piston to move. All right. So obviously, if we are not allowing the piston to move, the work done has to be zero, right? So that's a conclusion, because displacement work is equal to P into delta V. And if delta V change in volume is zero, then obviously work done is going to be zero. So if I write the amount of heat that's coming out from this gas is, let us say, delta Q2. So I get delta Q2 is equal to delta U2 plus delta W2, right? But we know delta W2 is 0 because the piston is not allowed to move. So I get delta Q2 is equal to delta U2, fine. But is this the expression that I want? Because I need the differences. But one thing interesting that we can note from here is that the condition in this is that the gas is being cooled from 100 degrees Celsius back to 30 degrees Celsius, right? So the gas is brought back to its initial condition. So if you see internal energy, the interesting thing about internal energy is that it only depends upon temperature, right? So if I write the expression for internal energy, if delta UF I have to write, I can write it as NCV delta T. So it only depends upon the temperature difference, right? So in first case, when we are heating it, then what happens is the internal energy increases. And second case, you're cooling the gas. So what happens is the internal energy decreases. Since the temperature difference is same, that's why what will happen is the amount of increase in internal energy for the first case will be equal to exactly the same amount of decrease in internal energy for the second case. That means that I can write this as equal to minus of delta U1, right? So this is very interesting to note, right? Now, in my question, it was asked mod of delta Q2, Q1 minus delta Q1 minus mod of delta Q2 is what is asked, right? I've already calculated delta Q1, so I need mod of delta Q2. So if I put a mod over here, I can write it in form of delta U1 as delta times of U1, right? Now, all I have to do is plug in all these values, right? So the expression that was asked in the question was, what is the value of delta Q1 minus mod of delta Q2, right? So I just have to put the values. That's equal to, so delta Q1 was equal to delta U1 plus 136 that we have already calculated, and delta Q2, mod of delta Q2 was equal to delta U1. With a minus sign, I put over here minus sign, and delta mod of delta Q2 is delta U1. So if I do that, this delta U1 and minus delta U1 gets cancelled, and we end up with a final answer 136 joules. And 136 joules is the correct answer. So in this question, we are given a cyclic process, okay? So in this cyclic process, we are asked, during one of the parts, we are asked to find the work done. Now, the interesting thing to note in this problem is that they have told us that during the entire cycle, 1000 joules of heat is rejected. All right. So these are the informations that's given to us, and we have a graph of temperature versus volume. Okay. So we have to observe this graph and we have to solve this problem. Okay. So let's get started. So if you see, the first thing that we observe is that it is a cyclic process. Now, for cyclic process, we know one thing, that delta U for the entire cycle has to be equal to 0, right? Delta U is 0. So if I write the first law of thermodynamics, I can write delta Q is equal to delta W, because delta U is equal to 0, right? So I can say for the entire cycle, the amount of heat that's rejected is equal to the total work done during the entire cycle. So the total amount of heat that's rejected is 1000 joules. So I should put it with a minus sign, because this is the amount of heat that's coming out of the system, which is equal to work done during the entire cycle. So work done from A to B plus work done for this process BC, and then work done for this process CA, right? Okay. So what we are asked in this question is, what is the work done during this process B and C? So this is what is asked, correct? So we know that the total amount of heat rejected is 1000 joules, and all we have to calculate somehow is work done during AB and work done during CA. Fine. Now, if you observe this graph properly, you'll notice that this process CA is a constant volume process, right? Because the initial volume and the final volume does not change. Now that makes our life very simple. Why? Because the work done during an isochoric process is 0. So CA is basically an isochoric process or a constant volume process. So the displacement work will be equal to 0. As you know, the work done is equal to PdV. dV is equal to 0. The change in volume is 0. So I can write that this work done during C and A, that process is 0. Fine. Now all I'm left with is work done during AB and work done during BC. So work done during BC is what I have to find out, and work done during AB, how do I calculate? Now if you observe this process A to B, it's a straight line, right? So it's a straight line which passes through the origin. Does it give you some amount of hint, or does it give you some hint? Let's see. So if I write this expression, PV is equal to nRT. So over here we see that there is a direct proportionality between temperature and volume, correct? So if I express that, if I want to write, let us say T is equal to some N, let us say this will be equal to P upon nR times of V. So T is directly proportional to V, right? So if this has to be true, then only we get a straight line, right? And if this is a straight line, then this expression, this value must be constant. Number of moles is constant, which is given to us as 1, all right? And the pressure also has to be constant. Why? Then only temperature will be linearly varying with the volume, correct? So if that be the case, then pressure becomes constant. For which process? For my process from A to B. Now, if the pressure becomes constant for my process from A to B, this process of A to B becomes an isobaric process. Now, if it's an isobaric process, I know the formula. Formula for calculating the work done during an isobaric process is P into V2 minus V1, right? Plus work done during BC is equal to minus 1000, right? But I don't have the values of volume. What I have is the values of the temperature. So this same expression can be written as PV is equal to nRT. So I can write PV2 is equal to nRT2 and PV1 is equal to nRT1. So I can write directly as nRT2 minus T1, right? And interestingly, all these two values are given in the question, plus work done during BC. The number of moles is given to us as 1, so I will just substitute as 1, and then we are left with R into T2 is 400, T1 is 300 plus work done during BC. This is equal to minus 1000. Cool. So what do we get? We get 100 into 8.31. If I plug in the value for R, plus work done by BC is equal to minus 1000, right? If I take it on that side, that will be negative, so it will give me work done by BC is equal to minus of 1000 plus, sorry, this will be minus of 1000 minus 831, right? And this will be equal to minus 1831 joules, and that is our correct answer. So this is a question of Carnot Engine, all right? So in Carnot Engine, we have source and we have sink. So the engine takes in heat from the source at a higher temperature and it rejects the heat at a lower temperature to the sink, right? So we have been told that there is a Carnot engine which works at these two temperatures. T1, the temperature of the source, is given to us as 127 degrees Celsius, and T2, which is the temperature of the sink, is given to us as minus 73 degrees Celsius. So we are told that there is some efficiency eta when it operates in this condition, all right? Then they change certain conditions and they want us to calculate the efficiency in all these different conditions, all right? So the first change is that they change the temperature of the source by 50 degrees Celsius, and they're asking that what will be this new efficiency, and they're calling it as eta 1, all right? And then what they do is they change the temperature of the sink by 50 degrees Celsius, and then they're asking that if eta 2 is the efficiency in this case, then what is the value of this eta 2 and how do we compare all the three efficiencies, all right? So we have got three particular cases, so we'll deal it one by one and we'll just get to find all the efficiencies in all different cases and compare them. So basically that's what the question says. So let's get started with the solution. So let us solve this problem, okay? So if you notice one thing, that the temperatures are given in degrees Celsius, right? But when we put it in the formula for efficiency, the temperature must be expressed only in absolute Kelvin scale and not in the Celsius scale. So don't make that mistake, right? So if I write the formula of efficiency, let us say in this case I'm writing this as eta 1 minus T2 upon T1, right? So first I have to convert this T2 and T1 in Kelvin scale. So how much will that be? So T1 equals to 127 plus 273, and that's equal to 400 Kelvin, right? And T2 will be equal to 273 minus 73, that's equal to 200 Kelvin. Now since I've expressed both these temperatures in Kelvin scale, now I can easily substitute it back into the equation of efficiency, and then I'll go forward to calculate the efficiency. So efficiency is equal to 1 minus T2 is 200 and T1 is 400, that's 1 by 2, which is 1 minus 1 by 2 is 0.5, that's equal to 50%, right? So eta in this case, we got it as 50%. Now let us say the next case, let us see what happens in case 1. So in case 1, they have told that they increase the temperature of the source by 50 degrees Celsius, but the sink remains the same. All right. So if I increase the temperature of the source, then my T1 will become 450 Kelvin and T2 remains same, right? So T2 is still equal to 200 Kelvin, right? Now I have to calculate the value of efficiency again. So in this case, let us say I call it as eta 1, which is equal to 1 minus T2 upon T1. And if I again plug in the values, 1 minus T2 is 200 upon 450. And if you just cancel and calculate, you'll get it equal to 55.5%, approximately 55% is what we can take, right? Now in the third case, we have told that the temperature of the sink decreases by 50, right? The temperature of the sink is decreasing by 50. And if the temperature of the sink is decreasing by 50, the temperature of the source remains the same. So in this case, I can write T1 still equal to 400 Kelvin and T2 is equal to 150, because T2 was equal to 200, right? And you're decreasing it by 50, so it becomes equal to 150. So now if I substitute the value of eta 2, I get 1 minus T2 by T1, which is equal to 1 minus 150 by 400. And when you cancel this and you calculate this value, you get approximately equal to 62.5, approximately this percent, right? So we have calculated eta. We have calculated eta 1 for the first case. We have calculated eta 2 for the second case. And if you see the values, you know that eta 2 is greatest, right? So eta 2 is maximum, then comes eta 1, and then comes eta. So I can write this as eta 2 is greatest, then comes eta 1, and then comes eta. So this is the correct option. So in this question, we have been given an expression for internal energy, small change in internal energy, all right? That's du equals to n times of PdV plus VdP. That's been given to us. And we also have the value of gamma for this process, and it's told that this is an adiabatic process. So the value of gamma is 4 by 3, right? So we have got basically three informations. The first one is the value of gamma. The second thing is it is told that this is an adiabatic process. And third is the most important part, that's the expression of internal energy, the small change in internal energy, du equals to n times of PdV plus VdP. Now what is asked from us is that what is the value of n, all right? So this n is what we have to find out. So somehow if you look at this question, we have to move around the adiabatic process and somehow express the formula of internal energy in some form that's given in the question. And finally we have to compare them and we end up with finding the value of n. So that's what we are going to do in this problem. So we know that this is an adiabatic process. So if it's an adiabatic process, the general expression for adiabatic process is P V to the power gamma equals to constant, and gamma is given to us. So P V to the power 4 by 3 equals to constant. So this is what we know. Now in a normal adiabatic process, what do you see? So the expression of a normal adiabatic process, I can write it as, so delta Q equals to delta W plus delta U is the expression for first law of thermodynamics. Now if I go further, I know that the amount of heat interaction is 0 in case of an adiabatic process. So this delta Q will become equal to 0. Delta U plus delta W can be written as PdV, right? So that's the expression of PdV. Even I can write this delta U as du, right? I can write this expression of delta U for a small change as du equals to PdV. So du plus PdV equals to 0 is the expression that I get in case of a general expression of an adiabatic process. This is what I know. Now, for this particular process that's given in the question, I need to express somehow the value of small change in internal energy, that's du, right? And that we can get from this expression. Now, so how we should begin? First of all, I need to put this in linear powers of P and V, right? I have to express it in form of P and V. So how do I do that? If I take log, I can write it as ln of P plus 4 by 3 ln of V equals to constant, right? Now, if I take the LCM, I can get 3 ln of P plus 4 ln of V equals to constant. But I need to express the whole expression in form of something plus PdV because that's how the expression looks like in my question. If you see this expression, I have to express somehow. Finally, I need to come to this point where I can express the whole of the equation of this particular process in this format, right? Then only I'll arrive at the answer and I'll be able to judge the value of n, correct? So how do I do that? If I differentiate this term, because I need the terms of PdV and VdP, so if I differentiate this, I get 3 times of dP by P plus 4 times of dV by V equals to 0, right? Now again, if I take an LCM, I end up writing the expression 3V dP plus 4P dV equals to 0, right? So this is the expression that I get in differential form, right? Now if you compare it with the expression of a general adiabatic process, you see if I add PdV, all right, so the expression is du plus PdV. So I have got 4 PdVs over here. So if I rewrite this expression as 3VdP plus 3PdV plus PdV equals to 0, it is somewhat similar to this equation right over here, right? Which means if I'm adding PdV to certain expression, then that in case of an adiabatic process becomes equal to the expression of internal energy, and that I can say with comparison, right? So you're comparing these two equations basically. So if you look at that, I can write du equals to 3 times of VdP plus P dV, right? Now we got an expression of du for this particular process. We had been given an expression of du in the question. So du was given as n times of PdV plus VdP, right? So if you compare both of them, what's the value of n? It's pretty simple. N is equal to 3, and that's my answer.
For more videos and live lectures on the JEE, click on the subscribe button now.